So it's clear. Okay, so we've got proofs. So what are the proofs? So actually, what we would like to do is now just take a tuple. Okay, we'll call this tuple. Excuse me. Call this tuple du. Okay, and where mu would be. Excuse me. Mu would be a row. Okay, so it would be row mu. Okay. Now dmu, small d, would be a tuple of size 16. And we're going to be interested, I've got it written down here, but I'll do it again. We're going to be interested at the tuple at 16 points, where the points are going to be at these specific domain points. And the special thing about these points is that they lie on a coset. Okay. And again, a coset is like a translation of subgroups. It's like an affine set. Right, and we said that it needs to be of size 16, so this would be 15. Okay, so what we want to do with this 16 tuple, we want to do an opening proof for these 16 data points. Okay, and we want to do it for every 16 tuple. And in the original data and also in the interpolated data. Okay. But the idea is that if I am a user of these systems and client and I want a certain data point, then I can request that data point and I can receive it with a proof. And then I check it with the commitment and I see that I really have what I requested. Okay. And that's the idea. And we actually, the reason for concatenating 16 elements is just, I think, to maybe like decrease the number of proofs that we need to produce, right? Okay, so if we look at phi and psi, I think, right? What do we see? So we see that actually phi is 2m divided by L root of unity. So 2m is 8k divided by L is 16. So we get to 512 root of unity. Okay. And then the other one is simply 16. Okay. And like Tomer mentioned before, they're all like basically outcomes of the same, like the smallest root of unity, okay, which is omega, right? We said that omega to the 8k equals 1. So like they're all consistent with that omega. Okay. And actually, if you look at equation 34, right? Equation 34 is basically just a multi-reveal equation, okay? So if I take d mu of x, okay? So that's the whole row, okay? That's actually the polynomial of row mu, okay? Because d mu of x is the evaluation in point x, okay? So it's the whole low degree extension of row mu. If I decrease from it a remainder polynomial, okay, that is actually just the quotient of du, okay, with those like that polynomial of the size 16 or order 15 of actually those evaluations that I want to reveal, right? If I actually divide it and I get left with some remainder, right? So that's this remainder polynomial. I'm not going to get into exactly how to construct it. And then I want to divide it. I actually I want to divide it by this, right? By the following, right? Phi k and then x minus phi k psi and like the vanishing polynomial of this domain that I'm interested in, right? And this is 215, I guess, right? So that's just what I had up here. This thing would give me a quotient, right? That I would call k q mu at k and x. Okay, so it's the quotient when I divide by this polynomial in point k, this 16 or this 15 order polynomial, but the one that matches tuple number k, right? So that's the quotient polynomial that I would get. And actually we know from like a basic identity, right, that this is equivalent to x to the L minus phi k to the L, okay? That's just an identity, and that's how I get the Q polynomial. And the other thing that I will now say that I'm going to define just this operator, which is pretty, I think, natural, okay? But I will say that actually qk, I would forget about this remainder polynomial, but not entirely. So I would say, actually, I don't even need to see this. But I would mark it as like the lower or the floor of this operation, okay? And the floor basically means that if I do this operation, I get rid of any negative powers of x, okay? That's simply what it means. But you can think about it like if it's the equivalent of if I was if this was integers, and then the division would have given me fractions, and then this fraction, right? If I get rid of it, that's how I do it with the floor operation. So we can think of the remainder polynomial as just what I need to write of that, like the remainder polynomial divided by the vanishing polynomial is essentially this fraction that I'm flooring. Okay.
Why is it different then?
Why is what different?
Than the first expression.
It's the same.
Okay.
I'm just saying, no, it's exactly the same. This is just the notation that I use. It just makes it easier. Also, when you calculate the quotient, you actually calculate the quotient directly. You don't need to calculate the remainder polynomial and subtract it, and you calculate the quotient, and then you just stop when you get to Okay, and equation 35 that I'm not going to go over basically just says that if I'm as the prover, actually Q of x, right, is what I'm going to want to give as the proof, and then if the prover has basically like I sample Q at the secret point. That's my proof for this tuple. And then if I have the proof, I have the commitment, everything else is a verifier I can do myself, and I can use this pairing equation to actually verify, and that's beyond the scope of today. So I'm going to now just concentrate on how do we efficiently produce these proofs, okay? So I think naively we could say, okay, just produce all of these polynomials and then just sample them all at S, right? So these polynomials you would have, first of all, the size of these polynomials is not so small, but even so, even if it was, you have like 512 squared of these polynomials, because you have 512 rows, and then we said that 8k divided by 16 is also 512. So you've got quite a few of these, okay? So it's a whole lot of these MSNs, which would tend to be quite heavy. Okay, so that's not an efficient way of doing it. Okay, so we're going to now present an efficient way of doing it, and this is based on the face Kvratovich scheme, also known as FK, the FK scheme, right, Kati? Okay.
Yeah, it's the face Kvratovich.
Yeah. Yeah. Okay. So, how does this work? Okay. So, I guess there is some intuition behind it, but the math tends to get a little bit like disgusting. So just try and follow with me step by step, and just make sure that you understand the previous step, and so that we can tie it like backwards and forwards. Okay, so if you look at equation 37, really, what we do here is actually we take equation 34, okay, and we basically plug it into itself, okay? So we actually make it into a recursion, okay? Now, how do we do this? So, you know what, maybe I'll write it out. So actually we've got mu k in x, right? And we can multiply it by xl minus phi kl, right? And that equals, we already saw d mu x, and this is just basically just a simple manipulation of line 34. And we will, for now, say we'll keep the remainder polynomial in place. Right, we can't use the floor operation right now. So if this is true, then we can go from here and do the following. We can say qkx, right, like let's do it like that. I'll take advantage of the ability to actually move stuff around here. So d mu x minus r ukx plus, and now I've got this bit from here. And this is actually not the way that the FK paper describes it. This is my way, but I think that it's that actually it's a much nicer way of doing it. And now if I just copy this, okay. Then what I can do is I can take this pad and move it here, and then, oops, sorry, and then do this, okay? So now I've defined it as a recursion, okay? And now I can get to the final pad, and I can actually, well, okay, so let's see. So moving from this to 36 is easy because that's just the floor operation, right? Because I just get rid of this remainder. But moving from 37 to 38 is maybe slightly less trivial. But the way to do it is to actually recast it into itself. Okay, so I'll just try and just do one recursion just to convince you, because it's not immediately immediately noticeable. Okay, and here we can do this. We can do okay, and then we can plug the same thing in. So here we could replug what we had before, and it would be d mu x minus r mu kx, right? Divided by xl, and then plus and and I could continue doing this pretty much forever, but I would stop when I start getting negative terms, right, in the x, because I'm not interested in the negative power. So now, if I actually go and say, okay, well, what am I really interested in, right? So I'm actually interested in the floor operation of this whole thing, right? And then when I go to the floor operation, I see that I can actually take, so this would be equivalent to the first term divided by the floor operation, plus then we're actually, I can take d mu x divided by x 2l, and I can actually take this vkl out, and you can check that this actually is equivalent. It's a bit of playing around with the floor operator to see really how far you need to go with it. Don't forget that the floor operation, I'm actually only interested in things that are powers of x. I'm not so interested in the constant terms, and that's why I don't actually mind I don't mind this term, right? I can take that out of the floor operation because it's a constant term, so it doesn't bother me, right? And that is pretty much it. Another thing to notice, if I look, and I'm not going to write this down, to look at equation 38, you will notice that actually, so the order of d mu x, right, we know is x to the power n, okay? Because, or it's actually x to the, sorry, the order is m minus 1, right? The degrees of freedom is m. So the highest monomial in d mu of x is x to the power n minus 1, right? So if I divide it by L, and then by 2L, and then by 3L, and eventually the number of additions that I get here is nearly m divided by L. M divided by L, I'll remind you, m is 4096 and L is 16. So I actually have 256, like 4096 divided by 16 is 256. But because the first term in the addition, right, which is this one, because that one is already divided by 16, you will notice that the number of terms in this addition is not 256, it's actually 255. Okay? Because if I were to add another term, the denominator of the next term would have been x to the power n. Because my monomial is x to the power n minus 1, I don't care about that term already when I do the floor operation. Okay? All right. So if that's true, then I would like to actually present equation 38 in a vector form. Okay, and that's exactly equation 39. Okay, how do I do it? So I do it again as the inner product between, and maybe I'll write it also in my notebook, right? I define the following vector, and this is, I did a bold d mu x. So bold d mu x, maybe I want to do a bold here. I'll just do underline d mu x. Okay. So underline d mu x is not the original polynomial, but it's actually a vector that is an outcome of the original polynomial. And it's a vector that looks like this. Okay. So it's actually an interesting thing. It's like a vector of polynomials. Okay. And then what happens, because I've only got 255 of these, right, because of what we mentioned before, and I would like to extend it to 256 for a reason that you will soon see. So this is actually 255. Actually, you know, yeah, this would be 255L. Okay. Then, in order to extend it to a power of 2, I just add a 0 at the end. Okay. And now, if I want to go back to equation 38, I need to actually multiply it with the following vector. I just need to multiply it with the powers of phi. Sorry. Yeah. This is actually, yeah, KL to KL. So notice that I actually didn't really do that much. And it's, I think, a little bit confusing, but not more than that. Okay. So when I actually do an inner product of these two things, okay, I end up with one polynomial. Okay, and that polynomial is exactly my quotient polynomial that I'm interested in. Okay. So up to now, I've done nothing. I've just rearranged, okay? But I'm still interested in the same quotient polynomial, right? So I call this vector phi, okay? Then actually q mu k of x is equal to vector d mu of x times phi, and of course, like whatever, like I need some transpose operation somewhere here. I say that I actually write it like in the document just to be consistent. So it's actually phi k transpose times d u of x. Okay, so that's actually nice because if you look at this, you can already note something. Okay, so you can. This isn't actually. No, this is fine. Sorry. Right. You can note that that actually the nice thing that happened here is that D is independent of K. Okay, that's the nice thing that happened here. And the other nice thing that happened here is that phi is now a vector of powers of some root of unity. Okay, I mean, we know which root of unity. It's actually, in this case, root of unity phi to the power KL, whatever it is. Okay. So the vector phi depends on K. It depends on actually the location of this tuple, and phi is a vector of powers of root of unity. So you can already understand that at some point we're going to take advantage of this by using FFTs to speed this process up. Okay, so the next thing that we want to do is, now that we defined actually this vector D and vector phi, we actually want to go, and we know that eventually what we need is actually like to sample these, the Q at the secret point. What we're going to do is we're going to actually do it in two paths. Okay, we're going to actually sample D, the vector D, at the secret point, and then from there we're going to get to Q at the secret point. Okay, so question 42 shows how we sample vector D, okay, at the secret point. And actually, vector D can be sampled at the secret point, okay, and remember that I'm trying to think how to so just to simplify this as much as possible. Okay, so when we look at say like the first term of vector D, okay, let's maybe just take the first one and then the rest will make sense, right? So if I take d mu x divided by xl, and then I do this floor operation, what do I actually do? So if d mu x, right, had coefficients, right, like d mu x is actually c0 plus c1x plus da 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 plus c, what is it again? Like 4095, I think, x to the power 4095. I don't have room. Right? Do you agree? If you don't agree, then tell me. Otherwise, I'll assume that you agree. Right? So if that's true, then actually this thing, right, is actually equal to let's see, so it's actually C in 16 would be, right, the constant, and then C at 17x, and then finally C 4095 x to the power of 4080, sorry, not, yeah, no, 79, right? I hope I'm not making these small mistakes, but I may be. So basically just minus 16, okay? So that's just what it means to take D and then, you know, like every time I divide it by some power of x, I actually just like sort of shift its coefficient in a way. Okay. Now, if I'm going to actually now sample each one of these floored polynomials at the setup, you can see that actually is equivalent to doing the following, and maybe I'll just do it as like let me just draw it as a matrix. So let's say that I had C0 to C4095. I hope that you're debugging me as we go along, because yeah. And then I would multiply it by like, so the first one, which is what I just did, by like, I'll have like 16 zeros here, and then I'd have, oh, sorry, this is not, I'd have something like, this would be 1 and S, and then S squared, right? And then whatever I get to. And then the next one would be like, instead of that, like 32 zeros, and then 1 and S, and okay? So, and then like this one would be, right, d mu x divided by x to the power L, and then this one would be d mu x divided by x to the 2L, and whatever, I'll keep going, okay? So I'll just give you a second to sort of like just see that you agree. Because this is like, I guess this is like a key point, and this is actually what's described by equation 42. Okay. Okay, so if that's true, then I think that there is a key observation here. Okay. And actually, the key observation is that if we look at, so C is just like a vector of coefficients from this matrix that we called C rows previously. What we can see here is if we have this big matrix that we maybe call S, this matrix has sort of has like a Toeplitz structure. Okay. Right. It's a bit of a weird Toeplitz structure, right? Because we're used to it. We're actually used to when we talk about Toeplitz, we're used to like maybe something like this, like A, B, C, D. And then I'm trying to do like, I mean, you know, like the same Toeplitz structure as what we saw here, right? It would be like maybe something like this, right? So you'd have like, right, this would all be zeros, and then I would have a structure like that. But it's similar to that, and actually, if you look closely, you'll see that what we're seeing is like sort of like a subset of the columns of another Toeplitz structure. Okay, so like I'm only taking like this column, right? I don't take this, and I don't take this, and then I take this column, and then again I skip a few, and I take another column, and right? And that's actually the structure to it. It's sort of like a subset of the columns of a Toeplitz matrix. Now, so we can say the following. We can say let's now call C mu. Okay, we'll call this, like this will be a vector, okay, and this is just the coefficients, C0 to C4095. Okay. And let's, we'll have, as usual, the setup. The setup will just be 1, S, okay, to S to the power 4095, right? It's the same setup. And you know what? Actually, just to make notation easier, I'll just call it S vector. Okay. But it's a secret setup, and it's actual it's group elements, right? It's on scalars. We understand it. So we can say maybe we do this. Okay, maybe instead of doing this matrix product where we have this Toeplitz matrix, maybe we do the following. Maybe we do a convolution of these two vectors. Okay. If we do a convolution of these two vectors, we know that the answer is whatever, some vector, okay, of group elements. And the size of it is actually going to be like something like 1 by, right, if this was 4096, it would be like 1 by 8191, right? Okay, that would be the full linear convolution. And by the way, if we slightly fix it up and we say, you know what, we want a convolution where we actually add a 0, okay? Because every convolution, if I want to stretch it to like, right, the size of each of the vectors is 4096, and I want to have like the result of the convolution that will be twice that, not twice that minus 1. I could always add a 0 on one of the sides, okay? That would be like maybe the, you know, the phase where they're completely like don't touch one another yet, okay? So let's say just for our notation that that we had that 0, and that 0 was added at the end, okay? Or maybe, you know, maybe I'll just write it like that. Maybe I'll write that we have the original convolution and then we add a 0 at the end. Okay. Now, look at what I want to do. So I want to actually take V, and then I want to subsample it. Okay. How do I or maybe I'll say just to sample it, right? Not to take like so V is actually like the size of this. Let's call this maybe V tilde. The size is from 0 to 8,191. So it's 8,192 samples in V. Okay. And I want to actually subsample it in the following samples. And now is when we need to be careful. We actually want to sample it. So the first sample, let's just remember, we want it to be this vector with the 16 zeros and then the setup, right? And we know that if we start from the beginning, like the first sample, the time that we will get to all the samples completely in would be 256. So I think that this will be like 256 plus 16, okay? Whatever it is, and then the next point would be 256 plus 32, and then I would continue until the last point that I want to sample V tilde would be this 0, and then this 0 would be at point 8,192. 1. Okay, if I start counting from 0, I think that is correct, but essentially, what I would like to do, the most important thing here, actually, sorry, this isn't 256. Sorry, you should have called me, but I guess that probably gets to be a bit confusing. But the length of the vectors here is 4096. So in the convolution, it would take me 4096 steps to get to the state when the vector C and the vector S are completely aligned, and then I would need to, from then, to jump in 16. So this would be 4096 plus 16, 4096 plus 32, and so on, until I get to plus, no, I do have a small misalignment here. It's 4095. And I apologize. This is just like a thinking exercise, so we don't actually have to you'll see that the end result is actually simple. But I want to go with you through the steps just so that you fully understand. But if we now go and count like the number of, let's try and count how many elements we end up with for V tilde. So actually you can see that what you end up with is exactly 4096 divided by 16. Okay? So the number of elements here, okay, is again 256, which is exactly what we wanted. Okay, I'll remind you that that the number of these floor elements that we wanted was exactly 255, and then we added a 0 at the end, and so with the added 0, it's 256, and that's what we get here, and that's actually this 0 is this artificial 0 that we added at the end. Okay. Now, so what we can do is we can say, okay, let's do the following. Let's actually define, if we have V tilde, right, and we want V tilde sampled at these places, then what we can do, we can do it in 2 steps. We can say, okay, let's take V tilde, okay, and then we actually downsample it, and I'll do it like that because I don't know how you actually mark that operation. We downsample it by 16, and we get some V hat. Okay, and V hat is simply just the 16th sample of V tilde. And then from V hat, we'll just select, right? So if we want like this V tilde at all these places, what we need to do is with V hat, we need to now just select it at something like, because obviously if we take V tilde and we downsample it by 16, we're going to get 512 points, but we don't want them all, so we only take from 256 to 511. Those would be equivalent to those at the top, right? So I actually change the order. I say, okay, let's sample it down by 16. And then once I've sampled it down by 16, I'll just take the second half of the samples. I'm not interested in the first ones. Okay. So how do I do this? To get to V tilde is easy, right? Because, actually, no, yeah, we'll stay here. So how do I get to V tilde? How do I do a convolution? What I can do is I can actually do a Fourier transform of each one of these vectors. Okay. Now, once I've done that, right, if I do a Fourier transform of each one of these vectors, I will get some other vectors. let's call them maybe, and I'm sort of out of names, call them just big C and big S. Okay, and here I can just multiply them. Okay, and then the multiplication, I can actually do an inverse Fourier transform, and then I'll get V tilde. That's my claim. Okay. But I don't want V tilde, right? I actually want a subsampled version of V tilde. Now, if you check the identities, you will see that if I need to actually subsample V tilde, right, that is equivalent to creating an aliasing in the original or in the Fourier domain. Okay, and this is exactly what I do. Okay, so we create an aliasing of these, of the Fourier transform of the vector S and the Fourier transform of the vector C mu, the vector coefficient. And once we create this aliasing, we Fourier transform it. We actually inverse Fourier transform it, and then instead of getting V tilde, I get V hat. Okay, and now I'm going to just maybe just write it out. Just a scheme, and you'll see if you'll tell me if you agree. So I now have big C mu, okay, which is a vector, okay, which is equal to the Fourier transform of small c mu. Okay, small c mu is really just the vector coefficients. Okay, and then I have this one. Okay, and this is the Fourier transform, and I hid one thing from you, and we'll touch on it in a sec. Okay, so if I have the vector of the setup and I Fourier transform it, I get like another vector of setup. And then what I can do is I can actually just do a Hadamard product of these two. And maybe we'll make it like that. Okay. And let's give this product a name. Okay, let's just call it I don't know, maybe epsilon. Okay. And now epsilon would be of the original length, right? So if C mu and S were 4096, right? Then epsilon would be 4096. But then I would define epsilon hat, which is, and I'm just going to like completely abuse notation, and I'm going to define this operator fold. It would be a folding of epsilon, meaning that I take epsilon and I fold it onto itself, okay, according to the length that I'm interested in, which was 512. And I fold it and sum it onto itself. And then I take epsilon hat and I actually do the Fourier -1 of epsilon hat. Okay. And this is quite a significant saving because epsilon hat is much shorter than epsilon. And it saves me, I basically just calculate the samples that I need. I only calculate this subsample sequence. I don't waste time calculating all these samples that I'm going to throw away anyway. Okay? So, do you know where I cheated you? Did you notice? Because I did cheat you once. No. Okay. So, throughout this, I made an assumption that is not true. And I actually made an assumption that in the Fourier transform, and if you look at like where it's highlighted, I made an assumption that I'm actually the result of the result of the convolution that I get from the Fourier transform is a linear convolution, but it's not. It's a cyclic convolution. Okay. So actually, this just requires a small change here. And it really requires that I don't Fourier transform this, but I Fourier transform a zero impeded version of these. So actually, the size here now is not 4096, but it's 8192. Okay. And when I fold, I still fold. I fold according to length of 512, and then this f minus 1 of epsilon is of length also 512. And from here, I actually select samples 256 to 511 because I'm not interested in the first ones. Now, we could also ask the following question, which I actually don't have an answer to, and I actually think that pretty sure it's not possible, but we can ask the question, is it possible to actually go down in the size even more? Because even here I see that I calculate 256 samples that I don't care about. Okay.
My question is, can we do like something to C and S so that we already get the folded epsilon when we is this possible? Maybe we can say
well, I mean, I guess that you can, right? You can let's see. We can definitely right in epsilon. This is actually big, right? Big CNS. We can definitely fold them prior to doing this element-wise product, right?
Yeah.
And if we're already folding them, then does that mean that we can actually subsample the original series before doing the Fourier transform? Exactly. Yeah. That does make sense. And the only thing that I'm a little bit wary about, I don't know. I think that maybe it's worth examining, but intuitively, I think that there's something problematic here because we saw that we actually started with convolutions that looked like these columns here, right? Mm-hmm. And you see that you need to use all the powers of S in these convolutions. And what happens when you actually subsample here, right? So you like get rid of some powers of S. So
yeah.
So something doesn't actually, in a way, I don't know. It doesn't make sense to me. But maybe it's worth looking a little bit deeper into this point. Yeah, we should consider it. So basically, that's what's done here. so this f minus 1 of epsilon actually is what we tried to calculate. It's this d vector u at secret point s. Okay. Now, if we
Oh, I see. Because of the because we multiply the multiplier.
it's not a multiplication. It's an element wise. No,
No, still, but when we multiply and then fold, we're taking the sum of products. When we fold and then multiply, we're taking the product of sums. It's not the same thing.
Okay. Sorry. But there may still be room for improvement here. I mean, this is like a huge improvement to the original naive scheme. This is basically, it's just a very, I think, nice way of mathematically showing the phased quadratic scheme. They showed it in an entirely different way, but it's the same scheme. Okay, it's the same original idea.
I'm supposed to stick with Homer now.
Can we? I mean, we're nearly done. Can you see if you can get 15 more minutes? Can we? Is it all right?
I'll check it out.
Okay. So maybe while Tomer is gone, I'm just going to show. There are a few other subtleties that I ignored. Well, the first one is, okay, so do we actually need to have these 8,192 FFTs? And obviously we don't, because again, we can actually do the FFT of the setup and then extend the FFT of the setup by doing this frequency modulation trick like we did before. Okay, we can do that. And then there is another subtlety that actually, because we're not actually, we did write here, we called this a convolution. It's another place where I sort of cheated you a bit, but it's actually not a convolution, right? It's a correlation because we're multiplying S0 by C0. We're doing it in order, not, we don't flip the order like we do in convolution. So actually that would mean that we need to have, we need to actually flip one of the sequences. And what I did here is I said in 43 and 44, I said that we take the reversed order of S. Okay, so we don't actually do an FFT to S, to the secret setup. We do an FFT to the reverse order of S. Okay, but those are just little details that are important in the implementation. They're not so significant to our presentation. And that's it. So now we've got vector D. You remember vector D was a vector of polynomials, right? And we've got it sampled at the secret point. So it's now just a vector of group elements, 256 group elements, where the last element is 0, right? Because we didn't really need it. Okay, now we're getting to what we wanted to do, and we don't want these D's, we want the Q's, right? We want the quotient of D divided by the vanishing polynomial, and we said before, if you remember, I'll just scroll back quickly, we said that this was a product of two vectors. One of them is D vector, which we now have at the secret point, which is good. And then another vector that looks like a powers of root of unity, okay? Where we have the other vector actually needs to run over K, okay? So K equals 0 would be the first tuple, K equals 1 would be the second tuple, K equals 2 would be the third tuple, and so forth, until we get to 512 tuples. Okay. So if we actually, instead of, maybe I'll do it in the notebook. So instead of doing what naively we would do is we would take d vector and we would multiply it by phi, right? Or maybe zero, right? Which would be the first one, and you know what? It's probably better to write it the other way. So we'd have right phi and 0 times d mu, and then phi1 times d mu, and then phi 511 times d mu. But if we put all the phis, and these are all transposed, put all the phis into a matrix, right? We would get the matrix whose rows are these phis. And then because of the structure of phi, you can already probably tell that this is simply another f of t. Okay, so that is exactly what's happening at the end. And maybe the final thing is that we know that d is of length 256 by 1. And we know that phi is of length 256, and actually the number here we've set to 511. Okay, and we see that we can actually here. So
we don't see what you're writing.
You don't. Oh,
Disappeared.
what?
Eh,
Yeah. This is really the final thing. So interesting. Okay, so actually, if we okay, I see that somehow it's disconnecting. I think that maybe we've got some issues with the Wi-Fi. But what we see here is that okay, I apologize about this. Yeah, I don't know. Okay, we'll try and just replace that. So we could, so here, right, or this is actually 512. Actually, this process is done per each row mu. Okay, so this is important, per row mu. Okay, so we repeat this 512 times. Now notice another 2 optimizations that we can do. Okay, one optimization says, okay, so you're actually you're creating these 512 essentially like sort of like FFT rows of a 256 length vector. So actually, if you think about it, you can create 256 and then interpolate them, right? In the same way that we did. So we can do like the first half, right? And then once we've created the first half of these proofs, we can actually create the second half of these proofs per row by basically just interpolating the first half. And it makes perfect sense because we said everything here is just a linear interpolation. There's nothing to it. So if we could interpolate the evaluations, we can interpolate the commitments, we can interpolate the proofs. So we can do that for every row. We can calculate the proofs of the first half and then interpolate the proofs for the second half. But then we can also do the same for the columns, right? Because we can do, instead of doing per row, per each one of the 512 rows mu, we can do the first 256 rows and then interpolate those proofs to the second 256 rows. And this is, here is a huge, huge, huge saving, because calculating these proofs is very, very intensive from an implementation perspective. You can see that besides the FFTs that we're doing, right, this fold operation, right, is sort of like a lot of these small 16 size MSNs, okay, because each one of each element of epsilon hat is actually an MSN of 16 values, because it's an addition of 16 values of elliptical curve, okay, where each one of these values is a multiplication of scalar by some setup element. So if instead of doing 512 by 512 in the final step, I do 256 by 256, and then I interpolate it to get the rest of the structure, it's nearly equivalent to doing a quarter of the work, okay? So this is significant. And that's all I have. So if anyone has any questions, ask now, and then I guess that's it. No?
Oh,
Hello? Huh?
that's cool. Okay, I guess you can't hear me very well again.
No, we can hear you.
So like I didn't see fully, like if you updated the note, like they use this Toeplitz matrix structure to pre-compute and stuff like that.
Yeah, there is a pre-compute. Essentially, line 43 and 44 are a pre-compute of the setup. So you actually like do like a FFT of the setup, and you actually do like it's an interpolated FFT of the setup, okay? Because you need to get.
You could do it like because I don't also like in general when you have like the roots of unity, what you said some time back, you have a roots of unity vector, and then you have a coefficient matrix which is in the Toeplitz form or triangular with some zero, and then you have the SRS vector, right? So this is like for one KZG opening at some root of unity, right? And when you have several such polynomials, you essentially batch them, right?
Yeah, so that's where the FFT comes in, okay?
So okay, so
Naively, you would calculate each one separately,
mhm.
okay? But then you would get to n squared, the like basically complexity of n squared.
Mm.
But we can lower it to n log n using using the FFT, because everything is linear.
Yeah. So like
Okay.
in general for each let's suppose say that like maybe this is something that I missed. So for each cell, right, like you need just one opening, right?
For each one?
For each row commitment you need just one opening, right? When you
Each,
come row,
each listen, each row has got one commitment.
right?
Each tuple within the row, and the tuple is 16, has got a proof, but it's a proof of an opening of 16 things. It's a multi-proof.
Okay.
Okay. Anything else?
Okay.
Okay, great. So Thank you very much.
Thank you.